In this subsection, we are ready to state and prove the quadratic reciprocity law. Let L and P be two distinct prime numbers that are both different from 2. The quadratic reciprocity law, due to Gauss, states the following. If we consider the Legendre symbol of L modulo P, and the Legendre symbol of P modulo L, you may wonder, what is the relation between these two quantities? The famous quadratic reciprocity law tells us that they differ by a factor of -1 to the power epsilon L times epsilon of P. At this point, some of you may not remember what those notations means, so let me quickly recall them for you. The Legendre symbol of L modulo P means L to the power P minus 1 divided by 2, which is plus or minus 1 modulo P. Remember, we first defined this Legendre symbol in the finite field Fp, and then extended to all integers, and the quantity L to the power P minus 1 divided by 2 is either plus 1 or minus 1 modulo P, because L to the power P minus 1 is always equal to 1, and the square root of that can only be plus minus 1. And the notation epsilon of L is L minus 1 divided by 2 modulo 2. Remember, this L is a prime number different from 2, so it is an odd number. So L minus 1 divided by 2 is an integer. And similarly, you can recall the definition for the Legendre symbol P modulo L, as well as the definition for epsilon of P. And now let us prove this. Let omega be an algebraic closure of the finite field Fp. And we pick an element little omega from omega to be a primitive Lth root of unity. So what does this mean? This means omega to the power L is equal to 1, and omega of L prime is not equal to 1 for any L prime less than L bigger or equal to 1. Now if X lives in Fl, the finite field with L elements, so you should notice the difference between these two. This is Fp and this is Fl. And this little omega is a primitive Lth root of unity. The element omega to the power x is well defined, since omega to the power L is equal to 1 in omega. And this omega is an algebraic closure of Fp. So it is safe to identify this element in the finite field with the integer modulo L. And therefore, we are able to form the Gauss sum y equal to the summation for all elements x in Fl, where each summand is the Legendre symbol of x given L times omega to the power x. And this Gauss sum plays a key role in this proof of quadratic reciprocity law. To continue the proof, we need two lemmas concerning this Gauss sum. The first lemma states that if we square the Gauss sum, then we will get something much simpler. Y squared is simply equal to -1 to the power epsilon of L times L. And here, by abuse of notation, L denotes also the image of L in Fp. So we are viewing this equation as something in the finite field Fp. So now let us prove this lemma. We'll begin by simply compute this y squared, making a few observations and transformations. So what is y squared? Y squared is simply y times y. And we write the first y just by its definition. And the second y is the same thing with the variable x replaced by z. And you will soon see why we are doing so. And first let us merge these two together. A generic term in this product of two sums looks like x over L times z over L times omega to the power x plus z. And here x and z ranges over the finite field FL. And now we are going to make a change of variable. We let u equal to x plus z and t equal to x. With this change of variable, the sum becomes omega to the power u, and this x is replaced by t, and z is replaced by u minus x, which is u minus t. And here, we sum over all possible choices for u and t in FL. But we are going to write this as an iterative sum. We can first sum over all possible values for t in FL, and then we sum up this whole thing for all u in FL. Because the multiplicity of the Lagrange symbol, we can put these two together. And we denote this equation by asterisk. Now concerning this part, let us do one more step. You see there's a variable t and there's a variable u. So the goal is to reduce this further and try to think of this as something involving only one variable. And to do this, we're going to pull out the t from here. And we are also going to pull out this negative sign. So here's the magic trick. Now if t is not equal to 0, this Lagrange symbol, t times u minus t modulo L, is equal to, now we pull out a negative t squared, and the rest is equal to 1 minus ut inverse modulo L. And again, we use the multiplicity for the Lagrange symbol to get negative 1 over L, t squared over L, and 1 minus ut inverse over L. From the computation in the previous section, you know, the first part is equal to negative 1 to the power epsilon L. And the second part, because the square here, this is a t over L squared, which is always equal to 1. So the second part is always equal to 1. And we copy down the third part. And we call this equation star. Now let's play with these two equations. We'll first multiply both sides of this equation with asterisk by -1 to the power epsilon of L. And then plug the star equation into the resulting equation. So in this step, we get and then if we plug this equation into here, what do we get? If you plug this guy into here, you see there's a -1 to the epsilon L, there's a -1 to epsilon L, so their product is always equal to 1. So they cancel out. We get from here 91 to the power epsilon L y squared. Notice that when t is equal to 0, this Lagrange symbol, by our convention, is always equal to 0. So the sum for that part is just over all t in FL star. We don't have to count that the case when t equals to 0, because that sum is equal to 0. And this -1 to the power epsilon L simply cancel out, as I explained before. And now let us simplify our notation a bit. Let C sub u be the sum of the Lagrange symbol 1 minus ut inverse modulo L for all non-zero t in FL. This is Cu. Then this becomes 91 to the power epsilon of L times y squared equal to the summation of Cu omega to the power u for all u in FL. So if you take this part to be Cu, then from here we get this simplified equation. And now let's look at the right-hand side of this equation. The terms on the right-hand side of this equation can be divided into two cases. If u is equal to 0, then what is C0? C0, by definition over here, will just be the sum of all 1 over L for t in FL star. And how many t's are there? There are precisely L minus 1 t's. And each 1 over L, remember by our computation in the previous section, each is equal to 1. So this is just L minus 1. And now, if u is not equal to 0, what do we have? We have this 1 minus ut inverse. We call this S. Because u is not equal to 0, it runs over FL minus 1. Because u is not equal to 0, so S is not equal to 1. So this thing will run over FL minus the singleton 1. And in this case, we have Cu, and now we plug in S equal to 1 minus ut inverse. We plug this guy into here. And Cu will become this sum, where S ranges over all of FL, including 0 and 1, minus the summand when S is equal to 1. And now we claim then this sum is equal to 0. So this thing is just equal to minus 1 over L, which is just -1. And now let me explain why this claim is true. This claim follows from the results of the previous section. The sum is equal to 0 because there are as many plus ones as negative ones. And why that? Why are there as many plus ones as minus ones? For this, you have to remember another interpretation for the Lagrange symbol S modulo L. Remember, we have a remark here saying that the Lagrange symbol is equal to 1 if and only if this number above is a square. And how many squares are there in the finite field? If you throw out the 0 element from the finite field, then there are as many squares as non-squares. And that is because of our theorem 4. Our theorem 4 part B says that if that prime number is not equal to 2, then the squares in the multiple subgroup of that finite field form a subgroup of index 2 in the whole group. So because it is the index 2, in that subgroup where you remove the 0 elements from the finite field, there are as many squares as non-squares. Using the language of Lagrange symbol, it means there are as many Lagrange symbols that are equal to +1 as -1. So this is due to theorem 4 on page 6 of Sayre's book. So there are as many +1s as -1s. So the sum is equal to 0. Now to summarize, the CU, namely this part, is equal to L minus 1 if U is equal to 0, and is equal to -1 if U is not equal to 0. So now we can simplify this equation to the following. When U is equal to 0, we have a term L minus 1, and omega to the U in this case is omega to the 0, which is just equal to 1. And for the rest, we are just summing over omega to the U times -1, and we pull this -1 to the front. And from here, we put together this -1 and the sum for all non-zero U's. So this simply becomes the sum of omega to the power U for all U in this finite field, no matter it's 0 or not. And this is a geometric sum. By the classical formula, this is equal to 1 minus omega to the power L divided by 1 minus omega. And because this little omega is a primitive Lth root of unity, so this is just equal to 0. Omega to the L is equal to 1. So this is equal to 0. And this is precisely equal to L. And now by multiplying both sides again by -1 to the epsilon L, we get precisely what we want. And this finishes the proof of the lemma. Now we state and prove our next lemma. Our next lemma states that if we raise the Gauss sum y to the power p minus 1, then it is equal to the Lagrange symbol of p modulo L. And now let's prove this. We begin by taking the pth power of the Gauss sum. And now let us recall the multinomial theorem. If you raise the sum x1 plus dot dot xm to the power p, then the expansion of the sum will look like the summation of the multinomial coefficient, where k1 plus dot dot km is equal to p, and each of them is non-negative, where this multinomial coefficient is p factorial divided by k1 factorial times dot dot km factorial. And this guy is divisible by the prime p unless one of k1 through km is equal to p. And this can be easily verified by the elementary number theory. Suppose k1 through km are all less than p. Because p is a prime number, if you factor out a p, then this thing will become p times p minus 1 factorial divided by k1 factorial through km factorial. And p minus 1 factorial divided by this is still an integer, because all the factors here are co-prime to p. P is a prime. Any integer that is less than p is co-prime to p. So this number is divisible by p, unless one of those k1 through km is equal to p. And it follows from this multinomial theorem that the sum is equal to just the sum of individual terms raised to power p. You can call this multinomial fractional string. And I have to emphasize, this happens in the field with characteristic p, or modulo p. And now we can further simplify this. Notice that by the assumption, p is an odd prime. So no matter if x over p is plus 1 or minus 1, x over p raised to power p is always equal to x over p itself. So we can drop this exponent here. And now here comes another magic trick. We're going to make another change of variable here. We're going to take z equal to x times p. And this z equal to x times p is in FL. And because p and L are co-prime, that means p is invertible in FL. So x is equal to z times p inverse in FL. So the equation above can be transformed as the sum of zp inverse over L times omega raised to power z, where z ranges over FL. And now, because the Lagrange symbol is multiplicative, as we have used before, we can factor out p inverse over L from here. And if we put this to the front, what do we have? We have just a sum of 0 L times omega raised to the power z. And that is precisely our y. So this is equal to P inverse over L times y. But what is P inverse over L? P inverse over L is precisely equal to P over L. This is because P inverse over L times P over L is equal to 1. So they are either both plus 1 or minus 1. To summarize, we have shown that y to the power p is equal to the rounded symbol of p modulo L times y. The thing we want to prove is that y to the power p minus 1 is equal to the rounded symbol p modulo L. So now it suffices to convince ourselves that y is not equal to 0 in big omega. Why is y not equal to 0? One way to see this is by lemma 1. By lemma 1, y squared is equal to negative 1 to the power epsilon of L times L. And this L is another prime distinct from P. L and P are coprime. So right-hand side cannot be equal to 0. So y cannot be equal to 0. Therefore, we can cancel y from both sides and get y raised to the power p minus 1 equal to the round symbol of p modulo L. And that finishes the proof of lemma 2. And now we can return to the proof of our main theorem on the quadratic reciprocity law. We look at the p minus 1's power of the Gauss sum y. On one hand, by lemma 2, this is on page 8 of Sayre's book, we just proved, y to the power p minus 1 is equal to the rounded symbol of p modulo L. On the other hand, this is equal to y squared raised to power p minus 1 divided by 2. And by definition, this is just the rounded symbol of y squared minus p. But by lemma 1, we just proved on page 7 of Sayre's book, this is equal to, remember the numerator is negative 1 to the power epsilon L times L. And using the multiplicity, this guy is equal to the product of negative 1 over p raised to the power epsilon L. And the other part is L over p. And this negative 1 over p is something we have already computed before. By theorem 5, on page 7, this guy is negative 1 to the power epsilon of p. So, putting all these together, we get the rounded symbol of P modulo L equal to -1 to the power epsilon P times epsilon L times the round symbol of L modulo P. And this is a quadratic reciprocity law. And you can equivalently write this as L over P equal to -1 raised to the power epsilon of P times epsilon of L times the round symbol of P modulo L. And this finishes the proof. And now let us make a translation of the quadratic reciprocity law. We write L capital R little p if L is a square modulo P. Remember, this happens exactly when L over P is equal to 1. And we can say this in another way. We say that L, in this case, is a quadratic residue modulo P. And if this doesn't happen, we write LNP. Using the language of the round symbol, LRP, if and only if the round symbol of L over P is equal to 1, and LNP, if and only if L over P is equal to -1. And if you look at this exponent epsilon P or epsilon of L, we know epsilon P is an even number if and only if P is congruent to 1 modulo 4. And similarly for epsilon of L. So this part is positive 1 as long as one of P and L is congruent to 1 modulo 4. And if they are both congruent to -1 modulo 4, then they are both odd numbers, and this product is also odd number. So this part becomes -1. And combining this with the language above, we have that the quadratic reciprocity law means that LRP is equivalent to PRL if POL is congruent to 1 modulo 4. And LRP equivalent to PNL, meaning in this case, this part is -1, if they are both congruent to -1 modulo 4. So this is a translation for the quadratic reciprocity law. One important application for the quadratic reciprocity law is that it can be used to compute the round symbols by successive reductions. For example, what is the value for 29 over 43, the round symbol? To compute this, we just keep using the quadratic reciprocity law. We can first flip them. I know there's a factor -1 raised to the power 29 minus 1 divided by 2 times 43 minus 1 divided by 2. And this is 14, so this term is just 1. So this is just equal to 43 over 29. And let's continue. Now 43 is bigger than 29. We can reduce this by subtracting a 29 from the numerator. So this is equal to 14 over 29. And now 14 is no longer a prime number. So we can factorize this into 2 and 7 and use the property that the Lagrange symbol is multiplicative. And by theorem 5 on page 7, the Lagrange symbol of 2 modulo 29 can be explicitly computed. It is equal to -1 raised to the power 29 squared minus 1 divided by 8. And what is this number? By computation, this number is -1. This is an odd number. So we get -7 over 29. And we use the quadratic reciprocity law again. We flip this. Now it's 29 over 7 times -1 raised to the power. Now it's 29 minus 1 divided by 2 times 7 minus 1 divided by 2. Again, this is 14, which is the even number, so this is equal to 1. So this is minus 29 over 7. And we can continue reducing this. This is equal to -1 over 7. And the last guy is just equal to -1. So this is an example illustrating how the quadratic reciprocity law can be used to compute the concrete examples of Lagrange symbol.